Hello everyone, welcome to the lecture series on analog electronics. This lecture series is a part of Let's Crack the Gate initiative by TEQIP Faculties. In the last few lectures, we have seen how a diode is constructed, how it works, what is the equivalent circuit of a diode, and how a diode behaves in circuits. So today we will discuss a special type of diode, and that diode is called a Zener diode. When we look at the characteristics of a diode, we know that it looks something like this. So this is the diode current and this is the diode voltage, and when the diode is forward biased, initially the current is very less, and as voltage increases the current also increases, right? So far we have seen how this part works, right, for a diode, how the forward bias condition works. Using this, we have already arrived at the equivalent diagram of a diode, right? So what happens in the reverse bias condition? We know that diode current, there is a diode current in reverse bias because of the minority charge carriers, and this current is very small, and once the reverse bias voltage reaches a particular level, this current suddenly increases, and we call this voltage breakdown voltage, right? We break down. But this special type of diode called Zener diode works in this region, that is in the reverse bias region. And for a Zener diode, this voltage is called Vz or Zener voltage, and this breakdown is called Zener breakdown. And if we want to make a diode work in this region, we have to reverse bias it. So Zener diode has a special construction, and it will work in the reverse bias region. Okay. Now this Vz can be controlled by controlling the doping of this Zener diode. So that is done in the manufacturing process, and the current corresponding to this voltage, which is also called knee voltage, breakdown voltage or knee voltage, and the current corresponding to that is called knee current, knee Zener current, that is IZK. Okay. So once the voltage reaches Vz and the current reaches IZK, the Zener is brought down, and when the Zener break down, what happens? The current suddenly increases, and Zener will act like a forward bias diode. Not exactly a forward bias diode, but it will have a high current. There is a maximum up to which this current can go, and that maximum current is called IZ max. So this is specified in the data sheet of a Zener diode. So Zener diode is a special construction, and it is operated in the breakdown region. Okay. So this is the practical diagram of a Zener diode, and when we go to the ideal case, the diagram looks something like this. When it is forward biased, it is suddenly conducting at 0 voltage because this is ideal Zener. It will remain in a non-conducting state in the reverse bias until Vz is reached. When Vz is reached, the current suddenly increases. In the practical case, we can see that there is a slope to this characteristics, but in the ideal case, the slope is infinity, and this voltage is Vz. Okay. Now if you look at this diagram, there is a slope here, and the slope is delta Iz divided by delta Vz, right? Change in current, which is because current is in the y axis, divided by change in voltage, voltage of the Zener. That is why I am using the term delta Vz. This is the reciprocal of a resistance, and that is the resistance of our Zener diode, that is 1 by Rz. Now RZ is the resistance of our Zener diode when it is working in the Zener breakdown region. Where can we use this Zener diode? The main application of Zener diode is as a voltage regulator, because when you look at the ideal case or even the practical case, the voltage doesn't change much and the current increases to a larger value. That means Zener diode can support a high current without changing the voltage across it very much. That means it can be used as a voltage regulator, and you know that a voltage regulator has constant output voltage. Now I told you about this IZ max. This IZ max corresponds to the maximum power that can be dissipated in the Zener diode, and this maximum power PZ max will be equal to the VZ value, which is the new voltage, into IZ max. Now if we look at the symbol of a Zener diode, it will look like this. There is a normal diode, and instead of drawing a line here, we will draw something like this, almost a Z. So this is the symbol of a Zener diode. If we look at the equivalent circuit of Zener diode, when it is forward biased, it is same as a normal diode. There is our Vt threshold voltage, or V gamma, we can call it Vt or V gamma, is the threshold voltage, and the average AC resistance, right? But we already know that Zener is not used in forward bias normally, it is used in reverse bias. That is, the anode of Zener is negative and cathode of Zener is positive. In this case, the equivalent circuit will look like this. The only difference is, now this is VZ and this is RZ. Okay, we have already seen what is VZ and what is RZ. Okay, so this is the equivalent circuit of a reverse biased Zener diode, and when you look at it, we can see that the cathode of Zener is positive, so this is actually the cathode and this is the anode. Now if we want to use Zener in a circuit, that is in its reverse bias condition, there are some conditions to be satisfied so that the Zener is turned on in the reverse bias condition. Okay, and those conditions for Zener diode operation or turning on of a Zener diode are: first condition is IZ, that is the current through Zener diode, must be greater than or at least equal to IZK, which is the knee Zener current. And the second condition is VZ must be, that is the voltage across Zener must be greater than or equal to VZ of the Zener. When these two conditions are satisfied, Zener diode will be turned on. Okay, so using this condition, we can make a voltage regulator. So voltage regulator using Zener diode. The circuit looks like this. Here is our Zener diode, and here we have our load, and this is our input V in, which is varying, and this is our load resistance, which is also varying. There is a resistance here called RS, and this RS is used to limit the current through the Zener diode. So here we have the source current IS, Zener current IZ, and load current IL. Now there are a few conditions you should know about. That is, this RL has a minimum value because this is a variable resistance. So RL can be a minimum or RL can be a maximum value. There is a maximum value for RL also, right? When RL is minimum, what will be the current? That is the load current through this RL, that will be the maximum current, because the Zener makes the voltage across this load a constant, right? The voltage cannot change because the function of a voltage regulator is to maintain the voltage at a constant value. So the voltage across Zener will be Vz, we know that. So when the voltage is same, that means when RL is minimum, IL will be maximum. When RL is maximum, IL will be minimum. So this is one condition you should know about. Okay. Now, when we look at the circuit, Vn is also varying. This is a varying potential. Our worst scenarios are when Vn is minimum and IL is maximum. So in order to get maximum IL, IS should also be maximum, right? So when IS is maximum, IL is maximum, there is a problem that IZ could go beyond its maximum limit. So we need to control this IZ below or equal to its maximum limit. So we need to design this circuit so that when the load is drawing maximum current through Zener diode can go maximum up to IZ max. Okay, but there is also one more condition, that if this Zener acts, if we need this Zener to act as a voltage regulator, the minimum current through Zener should flow. That is, IZ minimum should be at least greater than or equal to IZK. In that condition, the Zener will be turned on and the output voltage will be held to a constant. So when we design this voltage regulator, we need to remember all these things. Okay. The first condition is, for Zener breakdown, that is when the operation of Zener diode starts, IZ minimum must be greater than or equal to IZK, that is the knee current, right? Only when the current reaches knee current, then only our Zener diode can go into Zener breakdown. Also, we know that the value of IZ is equal to IS minus IL, right? You can see that IS is split into IL and IZ. That means IZ will be equal to IS minus IL. So in order to achieve this condition, we will assume that we have the worst scenario possible. Okay, that is 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 minimum and IL is maximum. This corresponds to the worst case for IZ minimum value, right? So what will be IS minimum? We know that for this to turn, when this is turned on, this voltage will be Vz. So IS minimum will be Vin minimum minus Vz divided by Rs. So we can write IS minimum as Vin minimum minus Vz divided by Rs minus, what will be IL max when RL is minimum, right? And the voltage across the load is Vz minus Vz divided by RL min. So this is equal to IZ minimum, and this value must be greater than or equal to IZK. Now IZK is defined in the data sheet of a Zener diode, and using that we can find out the value of Rs. Okay. Now our second condition is, IZ must always be less than or equal to IZ max. So we will look at the worst case scenario again, that is our IS will be maximum and IL will be minimum. That is the case when IZ could go maximum. This corresponds to IZ max. For IS to be max, Vin must be max. So Vin max minus Vz divided by Rs minus, for IL to be minimum, RL must be maximum. Vz divided by RL max. This will give us IZ max. Now we will do some problems to check our knowledge from the previous topics. Okay. So the first problem is this one. Assume that the diodes D1 and D2 are ideal in the circuit shown below. What will be the transfer characteristics of the circuit? That is, we need to draw the transfer characteristics of the circuit. So let's start there. That is, for transfer characteristics, we need the relation between V in and V out. Okay. Now if we look at the circuit, this is our V in. We have two diodes. Diode D2 has an anode connected to 5 volt. Diode D1 has an anode connected to V in. The cathode of diode D1 is connected to this point and the cathode of diode D2 is connected to this point, right? So as usual, we can assume that they are either short circuit or open circuit. So we'll go with the assumption that initially they are open circuited. So our equivalent circuit will be like this. Right? This is the anode and cathode of D1. This is the anode and cathode of D2. Now when you look at D1, we can see that the cathode of D1 is connected to 10 volt, right? This point is now 10 volt. So until the anode voltage of D1 is above 10 volt, D1 cannot be turned on, right? When we look at the diode D2, we can see that the anode of D2 is 5 volt, cathode of D2 is connected to 10 volt. So D2 cannot be turned on, right? Because anode voltage is less than cathode voltage. Cathode voltage is more positive compared to anode voltage. So D2 is open circuited and D2 cannot be turned on. So initially when these two diodes are open circuited, our output voltage will be 10 volt because it is clamped to this voltage source. So initially we have a 10 volt input. So this goes when Vin is negative also, because until the voltage at this point is greater than 10 volt, D1 cannot be turned on. So until then this condition prevails. So we have initially 10 volt at the output, whatever be the case input is. Now let's say input has become 10 volt. Okay. So when input is now 10 volt, now what happens? The anode and cathode voltages of D1 are same. That means a slight increase in input voltage can now turn on this diode. D2 is still reverse biased. So when this diode is turned on, what is the output? Output is now directly connected to the input. So output and input will have a linear relationship with a slope equal to 1. When input is beyond 10 volt, output is going to be same as input, and below 10 volt, output is clamped to 10 volt. Okay, clear? Now we can do the next problem. The input voltage in a 2-level clipper linearly increases from 0 to 150 volt as shown in figure. So this linearly increase from 0 to 150 volt. We don't know the time scale, so we will just have to draw our output corresponding to this input figure. Sketch the output voltage V out to the same time scale as input voltage. Assume that the diodes are ideal. Okay. So initially when we look at this diode, we can assume that they are open circuited. By now you must have understood that it is safe to assume that the diodes are open circuited when we start the analysis. So this is the equivalent circuit initially. This is our V out, V in, which is increasing linearly from 0 to 150 volt. This is diode D1, its anode and cathode. This is diode D2, its cathode and anode. This is 100K, this is 25 volt, this is 100 volt, this is 200K. Now when we look at diode D1, its cathode is connected to some voltage here. We don't know that voltage yet. If we want to know this voltage, we need to check D2 first. Okay. So when we look at D2, the anode of D2 is now connected to 100 volt and the cathode of D2 is now connected to 25 volt. So what will be the case of D2? Is it forward biased or reverse biased? Anode voltage is more positive than cathode voltage. That means initially D2 is forward biased. So D2 is now a short circuit. So this is the initial case. When Vin is equal to 0, at that point onwards, D2 is forward biased. So let me write that condition. Vin is equal to 0. D1 is off because it is reverse biased, and D2 is on because it is forward biased. We have already assumed that they are ideal. Now when D2 is forward biased, we need to find out the voltage here. Okay, let's call it V. So to find out V, we can use KCL. So let's say there is a current coming from here and it is going here. Okay, so 100 minus V divided by 200K, 100 minus V divided by 200K is equal to the current leaving this, so that is V minus 25 divided by 100 kilo ohm. So we can cut this, 2 is multiplied here, so 100 minus V is equal to 2V minus 50. Rearranging, 150 equal to 3V, that means V equal to 50 volt. Now the voltage here is 50 volt initially. Now what will be the output? Output is directly connected to this point. So V out will be equal to 50 volt when V in is 0. Now this condition is not going to be changed until this diode is turned on, right? So what will be the condition for diode D1 to be turned on? That condition will be when anode voltage of D1 is greater than 50 volt, right? So when anode voltage of D1 is greater than 50 volt, D1 is also turned on, and that changes this whole thing. Before we write this condition, we need to look into one more condition, and that condition is when D1 is turned on. Now D2 and D1 are in series here. When D1 is turned on, this voltage can be varied. So when this Vin increases beyond 100, this voltage will be above 100, right? When Vin is equal to 100 and D1 is turned on, the voltage at this point will also be 100 because this point is now directly connected to Vin, right? When the voltage here is 100, our diode D2 will be turned off. When the voltage here is more than 100, our diode D2 will be turned off because the anode of D2 is connected to 100 volts, right? We need to include that also in our condition, that is 50 less than or equal to Vin less than or equal to 100. For this condition, both D1 and D2 are on. When input voltage is above 100, this voltage at this point becomes above 100 and diode D2 will be turned off. Okay, thus this is the second case, when 50 less than or equal to Vin less than or equal to 100. This case D1 and D2 are on. When D1 and D2 are on, here also we have a short circuit. When this is also short circuited, now our output is directly connected to the input. So V out will be equal to V in. Now we know the third condition, right? When V in is greater than 100 volts. In this case, D1 is on and D2 is off. When D2 is off, now this is a open circuit. Now D2 becomes open circuited. Now our output is not connected to input. What will be the output? Output will be equal to 100 volt because it is clamped to this source. In this case, V out will be equal to 100 volts. So if we draw the characteristics of this circuit, so if we sketch the output voltage of the circuit, it will look like this. This is our input in time, this is V in, and this is our output time, this is V out. So input is linearly increasing up to 150. This is 150. Now we know that our input is now split into 3 levels. When V in is 0 to V in less than 50, what will be the output? Output will be 50 volts. When V in is between 50 and 100, output will be equal to V in, and when V in is greater than 100, V out will be equal to 100 volt. So we can see that this is 50, this is 100. So up to 50, V in is 50 volt. From 50 to 100, V in is, V out is equal to V in, and after 100, it is equal to 100 until here. Okay, this is 50 and this is 100. So this will be the output voltage. Clear? Okay. Now let's go into the next problem. Here we have a circuit which has a capacitor and a diode. What is the name of the circuit? It's called a clamper circuit. So we need to sketch the output voltage of the circuit shown below when this is the input voltage and this is the circuit. Let's do this. Now we need to check the conditions when diode is turned on, right? But this voltage is not sinusoidal. This voltage has two levels, on 10 and minus 10. Until now, we haven't seen any circuit operating in this type of signal. We have analyzed all the circuit using sinusoidal waveforms because that is the easier case. Okay. Now the input is a square wave. Let's see. When V in is equal to 10 volt, what happens to the diode? Pause the video and see what will be the output voltage. So when V in equal to 10 volt, this is plus or minus 10 volt. We know that the cathode of diode is now connected to plus 2 volt, anode is connected to plus 10 volt, and the diode will act as a short circuit. Now the capacitor is charged to some voltage here, right? So we will draw the circuit. Now the diode is short circuited. Our input is plus or minus 10 volt, right? Now what will be the potential here? It will be clamped to this 2 volt, right? Because output is now across this 2 volt. So this output voltage is 2 volt. Here we have plus 10 volt. And what will be the voltage across the capacitor? That will be plus or minus 8 volt. So the capacitor is charged to plus or minus 8 volt. And V out will be equal to 2 volt. So when the input voltage is 10 volt, output voltage is 2 volt. Second condition is when V in equal to minus 10 volt, right? There are only two levels, 10 and minus 10. When V in equal to minus 10 volt, we'll draw it again. Here we have our diode. Right? The capacitor is already charged to some voltage, plus or minus 8 volt. Now if we look at the diode, we can see that the cathode of diode is connected to a positive potential 2 volt, anode is connected to a negative potential. That means our diode is now open circuited. This is our V out, right? If this is ground, this is V out. So what will be the value of V out now? We can apply KVL here and we can see that minus 8 minus V out minus 10 equal to 0. That means V out equal to minus 18 volts. So this will be the value of V out. So when V in equal to 10 volt, V out is 2 volt. When V in equal to minus 10 volt, V out equal to minus 18 volt. Now this is our input. This is our input. And if we draw the output, when V in equal to 10 volt, V out is equal to 2 volt. When V in equal to minus 10 volt, V out is equal to minus 18 volt. So this will be our output voltage. This is 2 volt and this is minus 18 volt. Now you can infer something from here. In this circuit, that is in the clamper circuit, the peak to peak voltage of input and output remains the same when we assume that the diodes are ideal. Okay. Now our next problem, we have a circuit here. This is the first time we are going to do a problem like this. In the circuit shown below, assume that the voltage drop across a forward biased diode is 0.7 volt. That means this is a practical diode and it's a silicon diode. The thermal voltage Vt is equal to Kt by Q is equal to 25 millivolt. Okay. The small signal input Vi is equal to Vp cos omega t, where Vp is equal to 100 millivolt. Find the DC current and AC output voltage, which is VAC. Now, there is a new term called small signal input, right? Small signal input in this cases, this is a signal input and this signal input is a sinusoidal input. Okay. So, we need to find two things. First thing is the DC current, second thing is AC output voltage. Here we have our output voltage. So, when you look at the circuit, we have two sources, one DC and one AC. So, there will be a current through this circuit and that current will have two parts, one DC part and one AC part, because there are two sources. Now, you know superposition theorem. So, we will apply superposition theorem here and find out what is IDC and what is IAC, and then we will find out what is VAC, which is the AC output voltage. You also know that to apply superposition theorem, we need to remove one source and find out the current or voltage according to the other source. So, here also we will do the same. To find out DC current, we need to remove the AC voltage, which is Vi, input signal, right? So, how can we remove a source voltage? We will short circuit the voltage. If it was a current source, we have to open circuit it. So, in this case, we will short circuit this AC voltage, signal voltage, and then we will find the DC voltage, sorry, DC current. Okay. So, for DC current, this is a misnomer, DC means direct current only. Okay, let's write for IDC. We will remove the signal, so we have only our DC voltage, and there is the resistance here, which is 9900 ohms. This is 12.7 volts, and now the diodes can be replaced by their equivalent voltages, right? This is the DC equivalent voltage. So, each of this voltage will be 0.7 volt. This is given in the question, right? So, what will be the DC current in this case? IDC. IDC will be equal to 12.7 minus 4 into 0.7. There are 4.7 volts divided by 9900 ohm. So, that is 9.9 divided by 9900 ohm, that corresponds to 1 milliampere. Okay, so DC current is 1 milliampere. Before we find out VAC, we need to find out the average AC resistance of our diode. To find that out, we have already gotten Vt, which is Kt by Q, and that is equal to 25 millivolt. Now, we know the equation governing the diode current, ID is equal to ISc or Is into e to the power Vd by eta Vt. This we have already seen in diodes. Now, if we take the derivative of Id with respect to Vd, we get Is into e to the power Vd by eta Vt divided by eta Vt. This Vt and this Vt are the same, so we note it like this. Okay, so dou Id by dou Vd is Is into e to the power Vd by eta Vt divided by eta Vt, and we know that Is into e to the power Vd by eta Vt is Id only. So this is Id divided by eta Vt. Now, this is the reciprocal of a resistance, and when we take the reciprocal of the left hand side, dou Vd by dou Id will give us a resistance which is eta Vt divided by Id. Okay, and what is this resistance? This resistance is nothing but the dynamic resistance Rd. Okay, now if we redraw the circuit for small signal analysis, we have to remove all the DC values, DC sources. There is our input Vi, the AC input only, signal only, in the resistance 9900 ohm, and now the diode's DC sources, that is 0.7 volt DC, cannot be considered because that corresponds to a DC source, and in AC analysis we cannot consider them. So there is Rd only in the AC equivalent circuit of our diode. This is Rd, this is Rd, this is Rd, this is also Rd. Here we have our Vout or VAC, output AC voltage. Now, using this equation, that is Rd is equal to eta Vt divided by Id, we can find out the value of Rd. Rd will be eta Vt by Id. Now, eta for silicon is taken as 1. So, Rd will become Vt divided by Id. What was Vt? It is given as 25 millivolt. For most of the problems, the thermal voltage at room temperature can be taken as 25 millivolt. It is a derived value. 25 millivolt. And what is the diode current? That is the DC current. It is 1 milliampere. So Rd will be 25 ohms, right? So there are 4 25 ohms here. Now, what will be VAC? We can use voltage division rule. So VAC will be equal to Vi into 4Rd divided by 9900 plus 4Rd. That is Vi into 100 divided by 9900 plus 100. That is Vi into 100 divided by 10,000. Sorry, this is 100. Right? So this is cancelled. It becomes Vi divided by 100. Now, what was Vi? Vi is Vp cos omega t, where Vp is 100 millivolt. So that is 100 cos omega t divided by 100 millivolt. So what will be the answer? VAC will be equal to cos omega t millivolt. So this small signal analysis and how to do this, you should remember this. This will be a main part in transistor analysis. So you must remember how we did this. So let's do the next problem. This is a problem with Zener diode. Let Vz equal to 15 volt, that is breakdown voltage of Zener diode is equal to 15 volt. What is the power dissipation in the Zener diode? Okay. So this is the circuit. There is a 25 volt input and 150 ohm resistance here, 50 ohm resistance here, and this is our Zener diode. Okay. So we will initially assume that the Zener diode is not in its breakdown region yet. We need to find out whether Zener diode is in forward bias or reverse bias condition, and what is the voltage across the Zener diode. So we will assume that Zener diode is open circuited, and then try to find out what is the voltage across the Zener diode. Now this is the voltage across Zener diode. Let's call it V. Now what will be the value of V? V will be equal to 25 into 50 divided by 200, right? That is 25 by 4, which is equal to 6.25 volts. So Vz of Zener is 15 volt, and we know that if the voltage across Zener is not above 15 volt, Zener is not going to be in the breakdown region. So Zener is not in the breakdown region, so there cannot be any current through the Zener diode. So the power dissipation, if there is no current flow, then what will be the power dissipation? Will be 0 watt, right? Because Zener current is equal to 0 unless the voltage across Zener is greater than or equal to Vz, Zener cannot be brought into breakdown region. And also we can see that this is in reverse bias because the cathode is connected to a positive potential and anode is connected to a comparatively negative potential. Now the next problem, same structure, but only the output resistance has changed. It is changed to 850 ohm. Okay. Again, we will assume that the Zener is open circuited, then find out the voltage V here. So V will be equal to 25 into 850 divided by 850 plus 150. So 25 into 850 divided by 1100, and that will be 3 by 44, and that is 21.25 volts. This value is 21.25. That means our Zener diode is now in the breakdown region. But we also know that in the breakdown region, the voltage across Zener diode is a constant, which is 15 volt. So at this point, we have a voltage 15 volt, not 21.25. That is the voltage we got when we were assuming that the Zener diode is open circuited. But in the real cases, Zener diode is in the breakdown region, and this voltage is now tied to this potential 15 volt, which is the breakdown voltage of this Zener diode, the knee voltage of this Zener diode. Okay. So here the potential is 15 volt. Now we can see what are the currents through different branches. Let's say this is IS, this is IZ, and this is IL. What will be the value of IS? IS will be 25 minus 15 divided by 150 ohm, and that will be 0.06 ampere. What will be IL? It will be 15 divided by 850 ohms, and that is 0.0176 ampere. Okay. Now what will be IZ? IZ will be IS minus IL, and that will be 0.049 ampere. Okay. The current through Zener diode is 49 milliampere. The voltage across Zener diode is 15 volt. Now we can find out the power dissipation, Pz. Pz is equal to Vz into Iz. Vz is 15 and Iz is 0.049 ampere. Now that will give us 0.726. This is the power dissipated in the Zener diode. With that, I am winding up this lecture. We have seen diodes and Zener diodes. So the first portion of this lecture series is over, which was diode. From the next class, we will see what transistors are, how they work, and how we can use them in a circuit. Also, the analysis of circuits with transistors. Until then, bye.